Now, what we are going to do is what Sukriti already alluded to, which is that we want to solve this problem using some kind of a strategy, a search strategy. Now, the good thing is that there are many possible strategies here, and Sukriti mentioned only one of them, which is depth first search. And in fact, the first order of business that we have is to go over many search strategies and think about their strengths and weaknesses in the formulation that we have described. This is the first order of business. This will take our time today and probably part of the next class. And how do we evaluate how good a search strategy is? We will evaluate based on these 5 problem characteristics. One is completeness, one is time complexity, space complexity, another is optimality, and one is systematicity. So, let us quickly go over them. Completeness means that if there is a path to the goal from the start state, will it find it? There may be many paths, we are only interested in one of them. We may find a suboptimal path. For completeness, that is okay. But if a path exists, our algorithm should finally be able to find any one of them, and that is the notion of completeness. Fair enough? Time complexity you understand, space complexity you understand. We can say time complexity is number of nodes expanded or number of nodes generated. Space complexity is total number of nodes that I am storing in my memory, right. Notice I am saying nodes and not states, because we are in search nodes. We will now be looking at search nodes as opposed to world states, because a world state could come in many times. Now, in order to compute time complexity and space complexity, we will use 3 letters, 3 symbols, B, D and M. Okay? B is the maximum branching factor of the search tree. For 4 queens or n queens, it may be n, and for n puzzle, it may be 4. Okay? So, B is the branching factor. How many actions can I take in a given node, in a given state? Then M would be the maximum depth of the tree. Okay? The root is at depth 0, all the next states are at depth 1, the next nodes are at depth 2, and so on and so forth, and we will say that my maximum depth is M. However, M could be potentially infinite. And suppose I am not doing any duplicate detection in an n puzzle, is it infinite? Because I could do gap up, gap down, gap up, gap down, gap up, gap down, and I can keep doing this, and it will never end. So, I can technically have infinite depth in my search tree. And last but not the least, my algorithm may not know D, but for the purpose of analysis, we will assume that we are given a D, which is the depth of the least cost solution. So, it tells us that look, your goal exists at depth D, and it may exist later also, but it at least exists at depth D. So, the algorithm does not know it, but you know it for the purpose of analysis. So, we will compute time complexity and space complexity using B, D and M. Optimality is, does it always find the least cost solution, and systematicity is one unusual phenomenon, but it is an interesting concept. It says, do I visit every search node at most once, not state. Do I visit every search node at most once? Okay. Sometimes I may visit it multiple times, and then the algorithm would be called non-systematic, and we will see some examples. Okay. And we have to study breadth first search, depth limited search, iterative deepening search, and beam search as 5 uninformed search strategies. Okay. Now, we have already discussed this, but if our states are repeated, then my tree may become really large. For example, here is a simple example where there are 2 actions in A state, both lead to B, 2 actions in B state, both lead to C, 2 actions in C state, both lead to D, and you can see that when I create a search tree, I will keep replicating B twice, C 4 times, D 8 times, and I will create an exponential tree, even though my world state graph was linear. So, therefore, there are challenges with this, and then we can always do the graph search version of this, but there are other challenges that we will discuss later. But for now, we will keep this caveat in mind. So, let us come back to our n puzzle and let us see what we could do, and Sukriti's suggestion is the first suggestion that we would make, which is let us do depth first search. And let us say these nodes are A, B, C, D, E, F, G, H. Let us quickly see how we would do depth first search. So, what is the first node that we will go to? I need everyone to answer collectively. What is the first node I get to? A. After A, let us say I go to left. Okay. So, which node do I go to? B. Yeah, we go left. So, we go to B. Now, which node do I go to? Do I go to C or do I go to D or E in depth first search? D, right, because we are doing depth first search. This is something you know this, right? Depth first search goes depth wise. It first goes and completes the particular subtree and then comes back and backtracks. This is the definition of a depth first search. So, after B I go to D. Now, there is nothing else beyond D. So, what do? I backtrack. So, I backtrack back to B and then I go to E. Now, I have exhausted, there is nothing in E. So, I go back to B. I have exhausted B. So, I backtrack to A and then I go where? C, and then F and then G and then H. And at every point I go, I stop, I ask my domain designer's black box, is this a goal? Is this a goal? Is this a goal? And my domain designer says no, no, no. And eventually when you find the goal, it says yes, and then are you done? Our job was to output a path. Suppose G was the goal, what would you output? ACG, because we were interested in outputting a path. So far so good? Yes. Very good, very good. You are running ahead of me. What's your name? Vignesh. Vignesh is like, no, 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 this is not good. Depth first search may never end. And I said, wait, yeah, I am going to ask exactly that question. Is it complete? Think over it. If there is a path to the goal, will it always find it? How many people say yes? It's okay, you have to say something, it's okay to be wrong, nobody is judging. Think about it, how many people say that it is always going to find if there is a path to the goal? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many people think it will not find a path to the goal even if one exists? In a class of 150, we are at a 9 versus 13 or 14. Come on guys, you can do better. Okay, I am going to ask more such silly questions. I hope more hands get raised. Otherwise, I will pick on someone who is not raising their hand. Okay. Why would it not be complete? No, wait. Well, Vignesh should answer. Why would it not be complete? If the depth is infinite, okay, so let us take an example. We never return back from D, let us say, okay. The goal is G, but we never return from D because that subtree never ends. If that subtree never ends, will we ever find the goal? No. So, what if my search tree was finite? Then is it complete? Then it is complete. Very good. So, it is not complete because my depth can be infinite. Okay, what is the space complexity? We have to answer it in terms of time complexity. We have to answer it in terms of B, D and M. B, D and M. So, intuitively what is happening? How many nodes might I have under depth 0? 1. How many nodes might I have in depth 1? B, right, because I may have up to B nodes. How many nodes might I have in depth 2? B square. Okay. So, first of all notice the exponential characteristic of this. I may end up expanding many nodes as I go one depth further. Okay. One thing. Now, suppose my goal is at a low depth am I guaranteed that I will not be searching beyond that depth? Because suppose my goal is on the right subtree and I decided to go to the left subtree, then I need to spend all my time searching over the left subtree before I finally get to the right subtree. So, I have to basically search the whole of the subtree in the worst case, because in the worst case it is possible that my goal is the last node that I encounter in my graph or in my search tree. So, my worst case time complexity would be b to the power m. Because what is the full size of my search tree? It is b to the power m. So, this does not look very good, does it? What will be the space complexity? Now, this is very interesting. All right. So, let us have people. Why don't you raise your hands? Do some physical work. Yes, the person in the blue and red. Yes, what is your name? Naman. Naman says order M. Okay. Let us keep thinking about it. You might be right. Any other suggestion? Anybody else? Nobody else? If we do not maintain any stack, then it is M. If we maintain a stack, then what? If you maintain visited nodes, so for full duplicate detection or for what? Yeah, we are not doing full duplicate detection for now. So, assume ignore duplicate detection. Yes. Order b to the power d. Okay, why? Not known depth. It is the depth at which the goal might be. Might be found, right? It is the lowest depth. Yes. But we do not know d for the algorithm. It is only for analysis. Algorithm does not know d. Yes. Anybody else? b to the power m. What is your name? Vedant. Vedant says b to the power m. Any node that I visit, I should keep in memory. Is that what depth first search does? Why would it keep everything in the memory? It does not. What does it need to keep in the memory so that it can run the depth first search algorithm? Only the current path, but a little bit more. Let us think about that little bit more part. So, wait. Give me a second. Let us say we are here. When we realize that we have to backtrack back to B, we need to know that all of B's children have been explored. Fair enough? Because if it does not know that, it may go back to D and then keep oscillating between D, right. So, it needs to know that, oh, B has 2 children and both of them have now been visited, so that it can backtrack back from B. So, at every node in the path so far, I need to maintain all the children and whether they have been explored or not explored, or visited or not visited. Does that make sense? Similarly, when I go back to A, then I need to know that A should say, look, I have 2 children B and C, and B has been visited, let us go to C. So, therefore, how much space do I need to keep? What is my maximum length of the path? M, and for each node I have to keep how many children in the worst case? B. So, my space complexity becomes order Bm. Very good. So, what is your name? Rashi says Kranshika. Rashika. I thought AI systems become better at speech recognition. Looks like human systems are becoming worse. Kashika. Most speech recognition systems use a vocabulary that is given to them, so that they can pick one of those vocabularies words. In this case, your name was not in my vocabulary, so there was a problem. Okay, good. So, Kashika says if we could order all the nodes in some canonical ordering, then we do not need to maintain all the visited nodes, and that is absolutely correct. So, then you are changing the problem, you are saying not only do I know the children, but I also know some order, some canonical ordering of the children. So, if you are given that, you can get away with order M, you are correct. Okay, good point. Okay, so then so depth first search is deepest first, but what is an alternative? Breadth first search, right? You all know this. So, you know in what order am I going to execute? First I will have A, then I will have B. After B, what will I have? C, right, because I am going in breadth order. Once I have exhausted depth 1, then I go to depth 2. So, then I will have D, E, F, G, H, and at every point I will maintain a frontier, and this frontier will tell me all the nodes that I have not expanded so far. So, for example, after this I will have in my frontier B and C, then I expand B. So, I add D and E in my frontier, and so my frontier will look like D, E, C. Then I expand C, and then my frontier will look like D, E, F, G, H, right. So, this is how breadth first search works. Now, depth first search had a problem with infinite depth. Would breadth first search have a problem with infinite depth? Why not? Because we will expand all nodes of a certain depth before we start expanding any node in the further depth. Okay, it's an important point. So, now can we say it's complete? Yes, we will say it is complete because we will assume that B will be finite. Now, in most of AI, we are going to assume B is finite, because if B is infinite, we can't even go beyond first step in a search mechanism. So, therefore, AI systems were more focused on discrete problems as opposed to continuous variable problems. All the general principles apply, but the specifics become very different. So, therefore, we will for most part in the AI course will deal with discrete state spaces, and we will assume B is finite. Time complexity. Okay, so, now time complexity earlier was B to the M, because we said in the worst case we may have to expand up to depth M. Now, here what is the maximum depth we may have to expand until? D, right. So, we will have time complexity B to the D. Similarly, space complexity would be, now what about space complexity? In depth first search we had to only maintain the path, but in breadth first search we have to maintain the full frontier, and in this frontier how many nodes in the worst case might I have? Again all the nodes at depth D in the worst case, right. So, B to the D. And finally, is it optimal? See, we did not ask you the optimality question in depth first search, because if it is not even complete, then obviously it is not optimal, but now we can ask the question. How many people think it is optimal? Okay, good, more people are raising hands. How many people think it is not optimal? 1, 3, 5, 7. Why not? Person in the blue shirt, what is your name? Harish, yes, Harish. Why not? No, optimal not in terms of time complexity. The question about optimality is, if it finds a path, would it be the least cost path? That is the question. That is the meaning of optimality, that whatever path it returns, is it the least cost path to the goal? So anybody else who still thinks it is not optimal? Yes, what is your name? Saigwan, yes. Very good. Least cost and shortest path may not be the same. Cheapest is what we are looking for, not shortest. So, when would it be optimal? If there are no costs or equivalently all costs are the same. Very good. So, the slide says yes if step cost is 1, but basically we can say all the step costs are the same. Very good. So, now we have understood breadth first search. I will take 3-4 more minutes. I want to show you the next important algorithm and then we will come back to it later. So, the next algorithm is uniform cost search or the cheapest first. So, we want to solve this problem that it was not optimal, because if I have multiple step costs, then breadth first search may not always be the optimal solution. And so, we have a different algorithm called uniform cost search, which basically says expand the closest node first, cheapest node first, not closest, but cheapest, right, whichever has the cheapest path to that node, expand it first. So, I will start with A, but after A what will I expand? B. What is my decision, B or C, and which is cheaper? B, right. So, I expand B. Now, as soon as I expand B, I can now expand D, E and C, but D is at cost 3, E is at cost 7 and C is at cost 5. So, what do I expand? D, because that is the cheaper one, exactly, it is at cost 3. So, what will be next? C, right, because it is 5. What will be next? Come on guys, everybody, if you do not understand this, we will E, F, G, H, these are the 4 options we have. F, because its cost is 6, whereas the next better cost is 7. So, we expand F next, then E, then G and then H. Okay. Is this complete? Okay, this is a tricky question. The costs are integers. Okay, so yes and no. So, the only thing you need to ensure that costs are not 0, because if the costs are 0, then I may keep adding many infinite 0 cost edges and then I may get to non-completeness. So, that is a tricky subtle point, but as long as costs are positive, by the way costs are positive in all this discussion, and in fact negative costs create even more trouble. We will come back to that, or you will get that question in the exam. So, negative costs are actually more complicated, you think about why, we will discuss later. Time complexity, now this will be tricky for you. So, I will not ask you to come up with it, but let us say my lowest cost, the lowest cost is epsilon and my cost, the optimal cost is C star, then you can prove that your time complexity would be order b to the power C star by epsilon. Similarly, for space complexity, and this one is optimal even for non equal costs. So, before I stop, I want to show you 2 videos. These videos will give you a quick understanding about how depth first search and breadth first search work. So, this is how depth first search works. It starts from the start state, and let us say this is the goal it has to go, and it is taking some random action, it has no information about where the goal is. So, it has started from here, it needs to go here. So, it keeps searching and it keeps searching, and when it can't find anything, it backtracks. As you can see, somewhere it backtracks, like for example, it reaches this particular hole, it does not know what to do. So, it starts to backtrack and it keeps going and going and going. And now notice that even for this simple problem, M is pretty high, the maximum depth is pretty high of the search tree. So, therefore, if it has made a wrong decision for the then it will find very hard to come back and find a path that can reach that particular goal, right. This is how depth first search is working. It just makes some random call and says I am going to go there, and now I can go somewhere else, I am going to go somewhere else, and it keeps doing it, then it can't go anywhere else, and it keeps backtracking, and then it goes somewhere else, and it keeps doing that. So, can you guess what is going to happen here? Is it going to find the path or not? Yes, because my search tree is finite, my M is finite, right. We are doing full duplicate detection here. But oh, it found a way to go out of this hole. No, not yet. Now, also notice what this green shows. This green shows the path found so far. So, now it suddenly goes around it and it might find an alternative way to reach this place. And even if it finds it, what path would it output? This complicated path to reach the goal, and which is why we said if it finds an answer, it is not going to be optimal. And if you had an AI system returning that particular path to the goal state, you will say that the AI system is quite dumb. On the other hand, let us also run the uniform cost search algorithm. The uniform cost search algorithm goes in all directions. It maintains this yellow thing which is the frontier, and it keeps expanding in all directions. And when it finally converges, it will reach the optimal path. See, here uniform cost search and breadth first search are the same because all costs are the same, right. Now, I can assure you that you are going to even get bored watching this. This is a full 2-minute video, but it gives you an intuition about what breadth first search does and what depth first search does. So, what have we been trying to do? Our goal has been to solve pretty much every problem in the world, and of course, not every problem is possible. So, we are interested in solving every deterministic single agent problem in the world for now. Okay. And in that context, we try to define a general definition of a search problem, right. What is the general definition? I will be given a set of states, I will be given a set of operators or set of actions, and I will also be given a test which tells me whether it is a goal or not and a start state. But I will not enumerate all the state space for you. Instead, I will give you the start state and I will give you a black box function called the evaluation function or the expansion function, not evaluation, expansion function. And given a state, if you give it this expansion function, it will tell me the next states you can reach from that particular state with the actions that are given in my system. Okay. And we discussed that if we are given such a problem, how would we solve such a problem? And we realized that this is nothing but a graph search kind of an algorithm in that is coming in like depth first search or breadth first search, and of course, you have all studied depth first search and breadth first search. So, I went over it too fast, but the main point is that in depth first search I take an action and I explore that subtree completely before I backtrack and get to the next action, right. So, if I made a bad move early on, then I will end up exploring a lot and possibly not get the right solution, the optimal solution. So, for example, we looked at this particular video where our goal is to go from this start state to this goal state, and the system starts by taking some actions, like it starts to go in this direction straight and so on and so forth, and then it backtracks from some place. So, these shaded regions are the regions where it tried to find a path to the goal from and it could not. So, it sort of backtracked, and it keeps doing this and it keeps doing this, and finally, it finds a path that can go around the start state towards the left, and then it finds a solution. I have stopped the video just before it finds the solution. And notice that the path that it returns is this complicated path. This is sort of the final path that it is able to return, this green line. And of course, that is highly dissatisfying, but there is one advantage of this, and the advantage of this is that it takes less space, although it may take a lot of time. Okay. On the other hand, we have breadth first search. Okay. and in breadth first search or uniform cost search, right. So, we also studied uniform cost search. This is an example of uniform cost search, which will end up being exactly equal to breadth first search, because all actions are equal, right. So, they are the same thing. So, you start with this start state and then you keep going, and at every point you have a fringe. Okay. The colors here, the red and the green and the yellow, they sort of tell you how far from the goal you are. And so, notice that all states which are one step away will have the same color, all states which are 10 steps away which will have the same color, all states which have 20 steps away will have the same color, and so on and so forth. And so, notice that it is going in all directions from the start state, and always looking at all the states that are possible in a certain fixed depth, because of which it keeps going from left to right to straight to whatever, all possibilities, and finally in the very end it finds a path. So, when you look at this, you realize that at least it is giving you the optimal solution, right. So, let us look at what is the final solution it finds. It will basically find the optimal solution, right, and that is great, at least it will find the optimal solution. But what will it have to do? At any point in time, it will have to at least maintain the whole fringe, and that fringe will be exponential sized, b to the d sized, right. So, we also did some time complexity and space complexity computations, and we realized that for depth first search, the time complexity came out to be exponential in the maximum depth of the tree, but the space complexity came out to be only linear, or sort of b into m, right, b times m, where b is the branching factor and m is the maximum depth of the tree. On the other hand, for breadth first search, we found time complexity and space complexity both to be b to the power d, where d is the maximum is the depth at which the first goal is going to be found, right. And we also studied uniform cost search, and there was a slight confusion last time. We discussed that for 0 cost edges, uniform cost search will not terminate, but that is not full story. In fact, a person came back at the end of the class and discussed, what about I have geometrically decreasing edge costs, like you have 1 and then you have half and then you have 1/4 and then you have 1/8 and so on and so forth, and if I will have to keep taking those edges, and it will take me infinite time to get to 2, whereas let us say the optimal path is 2.25, I never reach the goal on that trajectory, and he is right. So, therefore, uniform cost search, we typically say that there should be a minimum cost in the system, and the minimum cost should be positive. So, in this case, in this slide, the minimum cost is denoted by E, or sometimes we denote it with epsilon, and then we are guaranteed for it to be complete.